Every time we look at the stars in the night sky, they seem still, unchanging, and indifferent to what's going on our little planet. Sometimes we forget that stars are not small, bright dots, but huge balls of plasma, some much larger than the sun. Many of these are relatively young. Others are older in their final stage of life. Some are very quiet, but others are so violent that they tear apart the space around them. Among the stars you see every night, most of them are not alone. They have companions around them. From much smaller stars that orbit them to exoplanets very similar to the planets of our solar system. Although we see them every night, they are so distant that many may no longer exist. Yet they continue to illuminate our nights like cosmic ghosts, reminding us that nothing lasts forever. From this small planet orbiting an ordinary star, we have learned to read the sky as a map, to measure distances that cannot be put into words, and to understand that stars are much more than just twinkling dots in the sky. Every star we see is a real physical object with mass, temperature, history, and fate. The night sky is not a ranking of sizes or energies, but a map of coincidences. Distance, intrinsic luminosity, and position combine to decide which lights dominate our human experience. In this documentary, we will embark on a journey following those dominant lights, not to enumerate them as isolated data, but to understand them as stages of the same cosmic history. To cross constellations, see impossible worlds, and discover the mysteries that the brightest stars in our sky hold. We will travel from the nearest stars that rotate so fast that they deform, to supergiants whose energy redefines any human scale. We will know systems where stellar death has already occurred and is still present, and others where proximity raises an inevitable question. Could we get there one day? This journey will not only be spatial, but also temporal. Each star will show us a different phase of stellar evolution: youth, maturity, old age, and remnant. And in that contrast, we will understand that the universe is not static. Instead, it changes, ages, and transforms, just like us. The brightest stars in the night sky aren't just the most visible. They are cosmic beacons that allow us to read the history of the galaxy from a small planet orbiting an ordinary star. By observing them, we cease to be mere spectators and become readers of the cosmos. If you're ready, the journey begins now. Our first destination requires us to travel far to the south. In fact, for many observers in the northern hemisphere, this star never rises above the horizon. It is a hidden gem guarding the southern celestial pole. To find it, we must follow the winding path of the constellation Eridanus, the celestial river. The river meanders through the dark patches of the sky, twisting and turning until it terminates abruptly at a brilliant blue-white point. This is Achernar, the 10th brightest star in the night sky. It is an intensely blue star, bright and sharp, but reserved for one part of the world. Only those who live in the southern hemisphere can see it rise above the horizon. If you live north of latitudes like Dallas in Texas, Cairo in Egypt, or Tokyo in Japan, Echinacea never rises above your horizon. It remains forever hidden beneath the southern curvature of the Earth. Conversely, for observers in southern cities like Sydney, Cape Town, and Buenos Aires, Echinacea is circumpolar. It never sets. It circles the south celestial pole, a constant companion in the night sky. To find Echinacea, southern observers often look for the Large Magellanic Cloud and the Small Magellanic Cloud. Echinacea forms a bright, rough triangle with these two satellite galaxies. It is the lonely, bright anchor in a relatively empty patch of the southern sky, making it an essential navigational star for sailors and aerospace platforms alike. Its name means the end of the river, and for centuries it was a landmark for southern navigators as a solitary light marking ocean routes. At first glance, it does not seem strange. It's a static blue dot with nothing interesting. Nothing in its appearance suggests that we are observing one of the most warped stars ever measured. As we move towards Echinacea, something strange becomes apparent: the color. Echinacea is not white nor yellow, it's deep blue, which indicates much higher surface temperatures. A significantly more massive and more energetic star. But the really shocking thing appears when we start measuring its shape. Most of us imagine stars as spherical balls of plasma, similar to our Sun. Gravity pulls inward equally from all directions, creating a perfect sphere. However, Echinacea shatters this rule. We are not dealing with a slight distortion, but with a star that has almost completely abandoned spherical geometry. Echinacea shows us that not all stars are spherical as we thought. How far can that deformation go? It is not a sphere, it's actually a stellar ellipse, an object that looks stretched, as if someone had tried to pull it off in two opposite directions. Their immediate surroundings are not quiet either. Echinacea is a B-type main sequence star, specifically classified as B6VEP. The E stands for emission. Known for ejecting material from its equator due to extreme rotation. Some of its mass is not tightly bound to the star, but forms diffuse structures of hot gas that surround it intermittently. But the defining feature of Echinacea is its rotational velocity. Our Sun rotates leisurely, completing a spin once every 25 days at its equator. Echinacea, by contrast, is a celestial centrifuge. It spins at a staggering speed of approximately 250 kilometers per second, about 155 miles per second. This immense centrifugal force fights against the star's gravity, causing the equator to bulge outward significantly. This distortion makes Echinacea the flattest known star in the Milky Way galaxy. If you could view it up close, it would not look like a ball, but rather like a skittle or a doorknob, fat in the middle and squashed at the top and bottom. Its equatorial radius is approximately 35% to 50% larger than its polar radius. The extreme distortion of Echinacea leads to a phenomenon known as gravity darkening. Because the equator is bulged out much further from the star's hot core than the poles are, the surface gravity at the equator is weaker. Lower gravity means lower pressure and density, which results in a cooler temperature. The poles of Echinacea are compressed and closer to the core. They scorch at an incredible 17,000 to 20,000 Kelvin. They are the primary source of the star's intense ultraviolet radiation. The bulging equator is much cooler, estimated at around 10,000 to 12,000 Kelvin. This means that if you looked at Econar through a specialized filter, it would not be a uniform brightness. The poles would be blindingly bright white-blue, while the equator would appear significantly dimmer and redder by comparison. It is a star with a hot top and bottom and a cool middle. If we were in a spaceship next to this star, the experience would not be pleasant at all. The radiation is intense. Its intense blue light is not only aesthetic, it is a signal of extreme energy of photons, capable of destroying molecules and eroding any unprotected surface. For a long time, we imagined the stars as perfect spheres because it was a comfortable simplification. Econar destroys that idea completely. It shows us that stellar geometry is not a rule, but a fragile consequence of the balance between forces. When one of these forces, rotation, becomes dominant, the shape of the star changes. Here we understand something essential. The laws of physics do not seek beauty or simplicity, only coherence. If a star can exist, being ellipsoidal, warped, and ejecting its own matter, then the universe will allow it. Econar forces us to accept that what we usually call normal in astronomy is only a limited fraction of possibilities. This star is not a rare anomaly. It's a legitimate expression of how matter responds when allowed to spin too fast. After Econar, we can no longer look at a star as a geometrically perfect object. But what would happen to a planet orbiting this star? So far, no exoplanets have been confirmed around Econar, and unlike other cases, here the absence of detections says much more than a simple lack of data. Econar is a young, massive, extremely hot star with a violent rotation. Its environment is dominated by intense radiation and by the periodic expulsion of plasma from its equator. In such a scenario, the formation and survival of planets are particularly complicated. Any nearby planet would be exposed to radiation, capable of eroding entire atmospheres on relatively short timescales. Regions farther away might offer a little more stability, but even there, the star's dynamic history would cause any life forms to go extinct before they thrived. If planets exist around Econar, they would probably be extreme worlds, very different from the ones we know. Massive planets with dense atmospheres or even bare cores, orbiting at distances so far away that low temperatures would not allow the existence of liquid water. Econar reinforces an idea that will continue to appear on our journey. The stability we enjoy in our solar system is, in fact, an exception rather than the norm. Most stars are not meant to host quiet planetary systems. As we move away from Econar, its ellipsoidal shape compresses back into a deep blue dot. From afar, it looks like an ordinary star again, indistinguishable from so many others. But now, we know what it hides. Our journey has just begun, and we have already seen something we didn't even think was possible. A star that is not spherical. We already understand that rotation can completely transform a star. However, what comes next will add a new layer of complexity, because the next stop will take us to a star that is about to die. Leaving the Southern River, we travel to one of the most famous constellations in the sky, Orion, the Hunter. Orion dominates the winter sky, standing tall with his belt of 3 stars. But our target isn't the belt. It is the angry glowing eye on his right shoulder. This is Betelgeuse, the 9th brightest star in the night sky. From Earth, Betelgeuse cannot be confused with any other. Its reddish-orange hue immediately stands out in the winter sky, marking the shoulder of Orion, one of the most recognizable constellations in the entire celestial vault. To the naked eye, it is not constant. Its brightness varies over time, sometimes more intense, sometimes visibly dull. That variability, perceptible even without instruments, makes Betelgeuse appear alive, as if breathing slowly. It is not the brightest star in the sky, but it is one of the most expressive. Looking at it never gives the feeling of observing something fixed, but rather something alive. Betelgeuse is a star of staggering proportions and restless motion. Its size is a subject of constant study because the star pulsates. It literally breathes in and out. It is around 950 times larger than our Sun. Modern measurements, which combine radio observations and satellite data, put Betelgeuse at roughly 642 light-years, about 197 parsecs from Earth. Close enough to feel familiar in galactic terms, yet comfortably distant. Despite shining with the power of roughly 100,000 suns, Betelgeuse is relatively cool at its surface, with a temperature near 3,500 Kelvin, compared with the Sun's 5,778 Kelvin. That lower surface temperature gives the star its warm orange-red hue. Its enormous surface area spreads the heat thin, so the light we see is deep and mellow rather than white-hot. You don't need a telescope to appreciate Betelgeuse. In fact, the naked eye often gives the clearest sense of its color and place in the sky. To find it, look for Orion's 3 belt stars. Betelgeuse sits roughly up and to the left of that line for observers in the northern hemisphere, a warm orange beacon marking the hunter's shoulder. It also forms one corner of the winter triangle, an easy-to-spot asterism that links Betelgeuse with Sirius. One of the sky's most striking visual contrasts is the pair of Orion giants. Betelgeuse's mellow orange glow set against Rigel's electric blue light at the opposite foot of Orion creates a vivid, almost painterly contrast that is best enjoyed with the unaided eye. As we get closer, the classic idea of star begins to disintegrate. Betelgeuse is not a compact, well-defined object. It is a red supergiant. A star so massive that it is difficult to describe without resorting to extreme comparisons. If it were to take the place of Sun, its surface would extend beyond the orbit of Mercury, Venus, Earth, and probably Mars. But even that image is misleading. Betelgeuse does not have a well-defined solid surface. What we call surface is actually a gigantic diffuse atmosphere, turbulent and extended. Its red color is not a visual ornament. It indicates that its surface temperature is relatively low for a star, although it is still lethal from any human perspective. Red is the sign of an aging star, which has exhausted much of its core fuel and is therefore cooler than a star like the Sun. The environment around it is not empty either. Betelgeuse is shrouded in vast clouds of gas and dust, remnants of matter ejected into space. We are not dealing with a star surrounded by the black void, but with a star that overflows into its surroundings, leaving a visible trace of its slow death. A spacecraft orbiting Betelgeuse would experience the sensation of not being in front of a stable, fixed object as we see it from Earth, but rather of an object in motion, as if something extraordinary were happening inside it. This is because its surface is dominated by colossal convective cells, which means regions where hot material rises and colder material descends repeatedly. Each of these cells is so large that it could engulf Earth's entire orbit, causing the star to appear to boil slowly. This effect causes Betelgeuse to lose mass continuously through stellar winds that eject enormous amounts of gas into space, creating irregular structures that slowly expand around them. It is not a punctual ejection like those emitted by the Sun, but a constant loss, as if the star were fraying. That ejected matter is what in the future will enrich interstellar space with heavy elements, forming planets like Earth. The radiation here is not aggressive, but it is persistent and overwhelming. There is no clear edge where the star ends. Everything is atmosphere, hot plasma, and slow but unstoppable movement. Being close to it makes it clear that we are witnessing a star that is about to die in a tremendous explosion. Betelgeuse's behavior is a clear sign that it is about to explode in something astronomers call a supernova, a colossal explosion of unimaginable proportions. In this, all the materials that Betelgeuse formed throughout its life will be ejected into space, and at that moment, the star will die. The exact date of this event is not yet known, but it is believed to occur between now and the next 100,000 years. This contrasts with the popular image of stars as eternal symbols. Betelgeuse has been in the sky for as long as human records exist, yet it is temporarily closer to its end than many stars invisible to us. Betelgeuse reminds us that nothing in the universe is eternal, not even the stars. The universe does not conserve, it transforms, and it does so without immediate drama, but with inevitable consequences. As of the date of this video's publication, no exoplanets have been detected around Betelgeuse, and in this case, the absence is especially revealing. If Betelgeuse ever had a planetary system, that system would have been profoundly altered or destroyed during its evolution into a red supergiant. When such a star expands, its outer layers inflate and its surface gravity decreases. Nearby planets would be engulfed or vaporized, while those farther away would suffer unstable orbits, altered by massive loss of stellar matter and intense gas winds. As we move away from Betelgeuse, its enormous atmosphere is compressed back into a familiar reddish spot. From afar, nothing betrays the internal chaos, the loss of mass, or the approaching death. We only see one more star in Orion, motionless and bright. But now we know what it's really like. Our journey now continues with a new awareness. Some stars do not represent eternal stability, but transition. We leave behind a slowly fading star and move into a system where death has already occurred once and left a silent remnant. The course takes us to a closer star. If with Betelgeuse we learned that there are stars that are about to die, with the next star, we will learn that there are some that have already died a long time ago. Now we swing our gaze eastward from Orion to find his hunting dogs. While the greater dog, Canis Major, waits for later in our journey, we first encounter the lesser dog, Canis Minor. This small constellation is anchored by the eighth brightest star, Procyon. The name Procyon is Greek for before the dog. It serves as a cosmic herald. Procyon resides just 11.46 light-years from Earth. This proximity is the primary reason for its brilliance. While it is intrinsically luminous, it does not possess the raw, overwhelming power of a supergiant like Betelgeuse. Instead, its brightness is a gift of intimacy. To the naked eye, Procyon shines with a yellowish-white, stable and precise light. For observers in the northern hemisphere, Procyon rises in the east shortly before Sirius. Because of this, it serves as a herald, announcing the arrival of the great dog Sirius. This relationship is encoded in its very name and location. For centuries, it was seen as a fixed point, marking the change of season. Nothing in its appearance suggests that we are observing a system where a star has already died. As we approach, Procyon begins to reveal a disturbing truth. We are not facing a single star, but two. Procyon is what astronomers call a binary system, a system in which two stars orbit each other. This system is composed of Procyon A, a star somewhat larger and brighter than the Sun. On the other hand, Procyon B is a small, dense, and extraordinary object, a white dwarf. The remnant of a star that died long ago and left only a small, compact core. Procyon A is a relatively quiet star. Its color is yellowish-white, its size is moderate, and its energy is released in a constant, stable manner. Procyon A is what the Sun will look like in roughly 4 to 5 billion years. It has slightly more mass than the Sun, which means it burns its fuel faster. Procyon A has effectively finished fusing the hydrogen in its core. As the fusion fire dies down, the core begins to contract and heat up, while the outer layers puff outward. This is the subgiant phase. Procyon A is currently expanding. It is already twice the diameter of the Sun and is noticeably brighter. It is leaving the main sequence, embarking on a journey that will eventually turn it into a bloated red giant. In roughly 10 to 100 million years, a blink of an eye in cosmic time, Procyon A will fully enter its red giant phase. It will swell to massive proportions, likely reaching 80 to 150 times its current diameter. Its surface will cool, and its light will shift from white-yellow to a deep orange-red. Also, it will become significantly brighter, likely rivaling the current brightness of Betelgeuse. There are no extreme deformations or violent rotations like those we saw in Echonar. At first glance, it looks like a normal star. The real discovery is in his partner. Procyon B, on the other hand, does not shine like an ordinary star. In fact, for a long time, it was impossible to see it directly. It is a small object, comparable in size to Earth, but with a mass similar to that of the Sun. Its gravity is so intense that it compresses matter to the point that it defies intuition. Here, for the first time in our journey, a disturbing concept appears. a star can die without disappearing. Procyon b offers a glimpse into the distant future. It was once a star larger and more massive than Procyon A. Because mass drives stellar evolution, it burned through its fuel rapidly, swelled into a giant, shed its outer layers, and died millions of years ago. The white dwarf does not emit energy through nuclear fusion. Instead, it radiates intense heat, concentrated in a tiny volume. The gravity on its surface is so extreme that any nearby object would be crushed instantly. There is no free-flowing plasma and no visible blobs here, just crushing pressure from gravity and intense thermal radiation. Procyon marks a profound change in our journey. So far, we have seen a star deformed by rotation and another about to die. Procyon presents us with something different, a star that died a long time ago. Here, we discover that a star's death is not always a spectacular event. Not all of them explode as supernova or disappear in a final flash. Some simply slowly shut down, leaving behind a compressed, dense, almost eternal core. Procyon b is the corpse of a star that was more massive than the Sun, and that exhausted its fuel. This is our first direct contact with the Sun's inevitable future. In about 5 billion years, our own star will go through a similar phase. It will lose its outer layers and leave behind a white dwarf, small but incredibly dense, just like Procyon b. Procyon shatters another common idea, that stars are young or active while shining. Here, we understand that brightness does not always mean life. Some stars shine because they are alive. Others glow because they have not yet finished cooling after they have died. So far, no exoplanets have been confirmed orbiting the Procyon system. And again, the reason is revealing. Binary systems represent complex gravitational environments. The presence of two stars, one living and one dead, profoundly alters the orbital stability of any nearby planet. If Procyon had planets in the past, many likely did not survive the red giant phase that gave rise to the white dwarf. During that stage, Procyon b's progenitor star would have expanded dramatically, like Betelgeuse, engulfing or ejecting nearby worlds. Procyon is one of the easiest stars to identify, even from light-polluted cities. Procyon is a winter and spring star for the Northern Hemisphere. It is best viewed in the evenings from January to April. To find Procyon, begin by locating Orion and its 3 belt stars. From that familiar line, follow the belt downward and to the left until your eye is drawn to Sirius. From Sirius, shift your gaze up and to the left, northeast, and you will see a bright, yellowish-white star. This is Procyon. A quick check is to see whether it forms a nearly perfect triangle with Sirius and the red shoulder of Orion, Betelgeuse. Together, they make the well-known Winter Triangle. Because Procyon lies close to the celestial equator, it is visible from almost every inhabited place on Earth. A faithful companion to sky watchers from New York and London to Delhi, Sydney, and Cape Town. After undertaking our retreat, as we move away from Procyon, its light seems simple again. But now we know that this star contains a complete story: birth, life, death, and remnant. Our journey can no longer be limited to watching the stars shine. We now understand that each one is a cosmic biography of the universe's history. What follows will expand on this idea. We will leave behind systems where a star died silently to approach much larger stars, where evolution occurs on a different scale. The next stop will take us to a star that dominates the sky, not because of its proximity, but because of its age and colossal size. We return to Orion, but this time we look down to the hunter's left foot. In stark contrast to the dying red giant Betelgeuse on the shoulder, the foot is marked by a blindingly energetic youth. This is Rigel, the seventh brightest star in the night sky. Rigel is a blue supergiant. If Betelgeuse is a massive dying ember, Rigel is a welding torch turned up to maximum power. It is hot, incredibly luminous, and radiates energy with terrifying efficiency. Rigel is one of those stars that do not go unnoticed. It marks the foot of the constellation Orion, one of the most recognizable in the night sky, visible in both hemispheres. Its light is bluish-white, intense, and different from the reddish warmth of Betelgeuse. To the naked eye, Rigel seems to dominate its region of the sky with a silent authority. For millennia, Rigel was interpreted as a luminous point, a visual anchor within a constellation full of myths and legends. It does not flicker like the stars low on the horizon, but shines brightly as if it were closer than it really is. Today, we know that it is a very distant star. The first surprise when approaching Rigel is the distance. Although it shines brightly, it is more than 800 light-years from us. The light that reaches us from this star every night left Earth 800 years ago, long before Christopher Columbus discovered America, and almost at the birth of the Inca culture in Cusco, Peru. If Rigel were moved to the distance of Sirius, it would shine as brightly as the full moon, casting sharp shadows on the Earth and turning night into a strange blue twilight. Rigel is a blue supergiant. Its color suggests extreme surface temperatures, tens of thousands of degrees. But color is just the beginning. As we get closer, the scale becomes difficult to process. Rigel isn't just bigger than the Sun, it's extraordinarily larger. Current measurements indicate that Rigel is between 70 and 80 times larger than the Sun. To put it in perspective, if we were to place it at the center of the solar system, its surface would extend beyond the orbit of Mercury, perhaps even approaching that of Venus. Rigel has a very hot surface temperature, generally cited around 11,000 to 12,100 Kelvin. If Rigel replaced our Sun, Earth would be instantly vaporized. Even Pluto, at the frozen edge of our system, would be scorched to temperatures higher than the surface of Mercury. Their environment is not simple either. Rigel is part of a multiple system, with much smaller companion stars orbiting at great distances. All of this occurs within one of the most active stellar regions in the sky, Orion, a stellar nursery where stars are born and die. Here, we are no longer observing an isolated star, but a major player within a massive cosmic context. To be close to Rigel is to face an overwhelming reality. Its radiation is intense, penetrating, and impossible to ignore. The blue light it emits is sufficiently energetic to ionize gas over enormous distances. Any spacecraft in the vicinity, unprotected, would quickly be disintegrated by the constant stream of high-energy photons emitted by colossal stellar winds. These are not occasional flares, but a continuous flow of particles that move away from the star at enormous speeds, causing Rigel to lose a considerable amount of mass every second, pushing the star further and further to its death. Here, for the first time during the trip, we feel that we are in front of a star that shapes its environment on a large scale, altering the surrounding space. Rigel definitely breaks any human reference. Until now, we have seen deformed stars and dying systems in which death has already occurred. But Rigel introduces something new: the scale of the massive. Here, we understand that the Sun is, by comparison, a small star. Rigel is tens of thousands of times more luminous than the Sun. It shines approximately 120,000 times brighter than the Sun in visible light. Its energy output in a single second exceeds that of the Sun over an entire day. As a result, it shines brighter than many stars combined, so that we can see it as one of the brightest stars in the sky, although it is not a single star that is very far away. This shows that the brightest stars in the sky are not necessarily the closest. Rigel shows that a star can dominate the night sky even from enormous distances, as long as its energy is sufficient. On our journey, Rigel is the first object that feels so big, not just big, but too big for any everyday analogy. After Rigel, the universe no longer seems like a place that we can easily mentally climb. So far, no exoplanets have been detected around Rigel. However, the reason is more important than the absence of data. Rigel is a young, massive, and extremely luminous star. His life is brief in cosmic terms. If planets formed around Rigel, they did so under extreme conditions, and probably did not survive for long. The winds would sweep away nearby orbits. The distant ones would be subject to gravitational perturbations within the multiple system. Rigel reinforces an inconvenient truth. The biggest stars are not usually the best hosts for enduring worlds. Beauty and violence often go hand in hand. As we move away from Rigel, its light continues to dominate the dark background for much of the journey. Even when the distance increases, their presence is not easily diluted. We have crossed a critical threshold in our journey. We are no longer talking about sun-like stars or quiet futures, but about objects that we didn't even think possible. What comes next will take us even further. We will leave behind the violent youth of the blue supergiants to approach ancient, aging stars that have grown to colossal dimensions. The course is still within Orion, but the color will change. The next destination will show us what a star looks like when it ages and expands. Traveling north, high into the winter sky, we find the constellation Auriga, the charioteer. The charioteer carries a goat, and the eye of that goat is the star Capella, the sixth brightest star in the night sky. Capella is located approximately 42.8 light-years from Earth. It dominates the northern winter sky and is easily recognizable in the constellation of Auriga, the charioteer. From Earth, Capella appears as a bright, calm yellow star. It does not have the extreme color of Rigel or the deep red of Betelgeuse. Its charm is in its simplicity. At first glance, it appears as a single, luminous point with minimal flickering. For centuries, it has been a reliable reference for orienting oneself in the night sky, and nothing in its appearance suggests that it could be complex or interesting. However, as we get closer, Capella begins to challenge that first impression. What appeared to be a single star begins to split. First in 2, then in 3, and finally in 4. Yes, Capella is not a star, but a multiple system of 4 stars gravitationally bound. This system is dominated by 2 yellow giant stars, orbiting each other in a delicate gravitational balance, Capella A and Capella B. They are retired stars that have exhausted the hydrogen in their cores and have swollen to massive proportions. Capella A is a yellow giant star, has a radius of approximately 12 times the Sun's radius, while Capella B is a slightly smaller yellow giant star that has a radius of around 8.8 times the Sun's radius. These 2 giants are locked in a surprisingly tight orbit. They are separated by only about 0.74 astronomical units, roughly the distance between Venus and the Sun. They whip around each other once every 104 days. Orbiting exceedingly far from these bright giants is a second pair of stars, located about 10,000 astronomical units away, roughly a light year. This pair consists of 2 faint red dwarfs known as Capella H and Capella L. Both are red, cool, and dim dwarfs with sizes much smaller than that of the Sun, with a radius of about 0.54 times the Sun's radius. They take thousands of years to complete an orbit around the central giants, forming a surprisingly stable quadruple system. The central pair shines with the luminosity of 150 suns, while the distant dwarfs are barely brighter than a dying ember. This set of 4 stars orbiting one another is what we perceive from Earth as a single point of light. In Greek mythology, the star is associated with the goat Amalthea. When the supreme god Zeus was an infant, his mother Rhea hid him in a cave on Mount Ida to protect him from his father, Cronus, who had a habit of eating his children. In this cave, the divine goat Amalthea nursed the infant Zeus with her milk. One legend states that Zeus, playing with the goat, accidentally broke off one of her horns. This horn became the cornucopia, or the horn of plenty, which could be filled with whatever the owner desired. To honor his nurse, Zeus placed her in the sky as the star Capella. The nearby stars, the kids, represent her offspring. On the other hand, in Hindu astronomy, Capella is known as Brahma Hridaya, the heart of Brahma. For observers in the mid to high northern latitudes, like the UK, Canada, Northern Europe, and the northern US, Capella is circumpolar. This means it never sets. It scrapes the northern horizon in the summer and swings high overhead in the winter. It is a constant guardian, always visible whenever the sky is dark and clear. Conversely, this northern bias means Capella is invisible to much of the southern hemisphere. It cannot be seen from cities like Punta Arenas in Chile or Wellington in New Zealand. Here, a crucial idea is reinforced. What we see is not what we believe. The enormous distances between us and the stars create an illusion in which a system of 4 stars appears as one star from Earth. Capella is the first clear reminder that many stars are not alone. Being close to Capella is different from being close to Rigel. Here, we do not feel overwhelming violence or devastating radiation. We feel dynamic balance. The two yellow giants emit intense but softer radiation, closer to solar radiation, although amplified by their size. Their surfaces are covered by huge convective regions, bubbles of hot plasma that rise and fall slowly, much larger than those of the Sun. Because they are so close to each other, their gravitational fields interact, shaping material losses and creating a shared environment. The fate of these stars does not depend only on their mass or age, but on their relationship to each other. On our journey, Capella takes us from individual stars to systems which, no matter what happens, will share their fate. After Capella, we can no longer assume that a star is a single entity. Sometimes it is an entire family living in harmony in the universe. When we move away from Capella, its complexity is compressed back into a single yellow dot. From afar, nothing reveals the multiple four-star system or gravitational dance occurring there. This star has taught us to distrust what we see with the naked eye. But our journey continues, now with a new awareness. Glitter can hide smaller companions, but they are no less important. What follows will lead us to a star that does not deceive by its multiplicity, but by its symmetry and apparent perfection. A star that has been a reference in the sky for millennia, and that directly connects our journey with human history and the passage of time. Let's continue with the number 5 spot. We now shift seasons. We leave the winter constellations behind and look toward the summer sky. High overhead shines a star of piercing sapphire clarity. Vega, the 5th brightest star in the night sky. Residing just 25 light-years from Earth in the constellation Lyra, Vega is a piercing blue-white beacon that has served as a cornerstone of astronomy for thousands of years. It was the first star ever photographed, the first to have its spectrum recorded, and for over a century it defined the 0 point of the magnitude scale. If you say a star is bright, you are, mathematically speaking, comparing it to Vega. Yet modern science has revealed that this standard star is anything but standard. Vega is impossible to ignore. Finding Vega is effortless. In mid-northern latitudes during July and August, simply look straight up, at the zenith, around 10 p.m. The brightest blue-white star you see is Vega. Near it, you can find a small parallelogram of 4 fainter stars. The body of the Lyra is one of the vertices of the summer triangle, and for hours it seems to remain motionless, while the rest of the sky revolves around it. Since ancient times, many cultures have taken it as a reference point to orient themselves, because observing Vega was equivalent to observing a fixed point. To the naked eye, it looks like an ordinary simple star with no mysteries. But as we get closer, it begins to show its true face. It is a bluish-white star, hotter and more luminous than the Sun, but not as colossal as Rigel. It is roughly 2.1 times as massive as the Sun and only about 450 million years old. A chaotic youngster compared to our middle-aged solar neighbor. However, if you could travel 25 light-years and view Vega up close, you would not see a sphere. You would see a shape resembling a squashed beach ball or a thick M&M candy. Because Vega turns fast. Not as fast as Equinar, but fast enough not to be perfectly spherical. From Earth, we observe it almost directly from one of its poles, which misleads us about its proper shape. However, from other angles, Vega would be slightly flattened, with a cooler equator and warmer poles. Because we look at the hot pole, Vega appears brighter and hotter to us than it would to an observer looking at it from the side. We are seeing the star's good side. Its surroundings are clean, with no large nebulae nearby, but there is a clear sign of past and future activity, a disk of dust surrounding the star. This disk, detected in the infrared, is a remnant of material from collisions and formation processes that have not yet consolidated. Vega is not just a star, it is the center of an evolving system. In the history of science, few objects have been as useful as Vega. It is the metric system of the sky. When astronomers classify how bright a star is, they use the apparent magnitude scale. This scale is logarithmic and slightly counterintuitive. Lower numbers mean brighter stars. For most of the 20th century, Vega was arbitrarily assigned a magnitude of 0.0 across all wavelengths. If a star has a magnitude of plus 1.0, it is 2.5 times fainter than Vega. If a star has a magnitude of minus 1.0, it is 2.5 times brighter than Vega. Although modern, high-precision instruments have adjusted Vega's magnitude slightly to plus 0.03, it remains the primary reference star. When you look at Vega, you are looking at the standard candle against which the brightness of the entire universe was once calibrated. For thousands of years, Vega was the north celestial pole. The Earth's axis of rotation pointed almost directly at it. The stars seemed to revolve around Vega like needles around a nail fixed in the sky. For that reason, some ancient cultures placed Vega at the center of their celestial maps. Over the centuries, that role changed. Today, that place is occupied by Polaris, or better known as the North Star. But the movement has not stopped. The Earth wobbles on its axis like a dying spinning top, a process called axial precession. A full wobble takes about 26,000 years. In about 12,000 years, the Earth's axis will point towards Vega again. This does not mean that the star moves to occupy that place, but that it is we who rotate slowly, dragged by the precession of the Earth's axis. The journey ceases to be only spatial and becomes historical and temporal. Vega shows us that heaven is not eternal or immutable. In reality, it changes slowly over time. The stars we use today to orient ourselves were not always the same, nor will they be in the future. Vega reveals a powerful truth. Stability is momentary. Even stars and constellations are subject to the passage of time. Our place in the universe is not fixed. It moves, even if it is at a pace imperceptible to human life. Vega represents a different kind of possibility, not the immediate promise of life, but evidence of processes that with sufficient time can build complex systems. When we move away from Vega, its brightness remains constant for a long time, as if it refuses to disappear. This star has taught us to look at the sky like a slow clock, where references change with relentless patience. We understand that the stars not only illuminate space, but also history. Our journey continues, but now we will move into something closer, more intimate. We will leave behind the star that marked the axis of the sky to approach another that has already left behind its youth and expands towards its end. To find our next destination, we use a famous trick of the trade, arc to Arcturus. We follow the curve of the Big Dipper's handle, arcing away until we hit a brilliant orange star. This is Arcturus, the fourth brightest star in the night sky. However, for residents of the northern latitudes, including North America, Europe, and most of Asia, it is effectively the brightest star they can see, as the top three belong largely to the southern skies, or lie close to the southern horizon. Arcturus is also the brightest star in the northern celestial hemisphere. It resides in the constellation Boötes, the herdsman or bear driver, as it seems to chase the Great Bear, Ursa Major, around the pole. The journey to Arcturus feels different. This star is old. Arcturus is the closest and brightest example of a red giant, technically an orange giant, to Earth. Looking at Arcturus is like looking into a crystal ball that shows the future of our own sun. Arcturus is an old star, likely around 7.1 billion years old, older than our 4.6 billion-year-old sun. For billions of years, it fused hydrogen into helium, just like the sun. But eons ago, that fuel ran out. When the hydrogen in the core was exhausted, the core contracted and heated up, while the outer layers puffed outward. Arcturus has left the main sequence and is now in the autumn of its life. Arcturus has swollen to approximately 25 times the radius of the Sun. If placed in our solar system, it would swallow Mercury and extend roughly a quarter of the way to Venus. As it expanded, its surface cooled. Arcturus burns at roughly 4,290 Kelvin, compared to the Sun's 5,778 Kelvin. This lower temperature shifts its light spectrum toward the red end, giving it that unmistakable pale orange hue. Despite being cooler than the Sun, its massive surface area makes it incredibly bright. It shines with the luminosity of about 170 suns. Because Arcturus is relatively close, only 36.7 light-years away, astronomers have been able to measure its diameter directly. It was one of the first stars to have its heat measured. In fact, if you stand under Arcturus on a clear night, the heat reaching your skin from that single star is roughly equal to the heat of a single candle placed 5 miles away. It sounds negligible, but in the realm of astrophysics, that is a palpable connection. While most stars in our sky, including the Sun, orbit the center of the Milky Way in a fairly orderly flat disk, like cars driving around a racetrack, Arcturus is breaking the traffic laws. Arcturus is moving significantly faster than its neighbors. It has a very high proper motion, the apparent speed at which it moves across our sky. It is moving at roughly 122 kilometers per second, relative to the solar system. While most stars appear fixed in human lifetimes, Arcturus moves fast enough that in roughly 800 years it shifts the width of the full moon. It is currently almost at its closest point to Earth. In a few million years, it will have sped past us and faded into obscurity as it heads out into the galactic halo. Arcturus is not alone. It travels with a group of 50+ other stars known as the Arcturus stream. These stars share the same strange trajectory. They are plunging down through the galactic plane at a steep angle. Arcturus is arguably the easiest star to locate in the spring sky, thanks to a famous celestial roadmap. First, locate the handle of the Dipper, which consists of 3 bright stars. Notice that the handle is curved. Imagine a line extending from that curve. Follow the natural arc of the handle away from the Dipper. The first bright orange star you hit is Arcturus. Arcturus is the alpha star of Boötes, the herdsman. The constellation shape resembles a giant kite or an ice cream cone, with Arcturus serving as the pointy base of the cone. The name Arcturus is one of the oldest in the sky, derived from the ancient Greek Arcturos, in which Arctos means bear and Uros means guardian or watcher. Literally, it is the guardian of the bear. This makes perfect sense observationally. As the constellation Ursa Major, the Great Bear, rotates around the North Star, Arcturus follows close behind, as if chasing or herding the bear through the night. In mythology, Boötes is often identified as Arcus, the son of Zeus, and the nymph Callisto. A jealous Hera turned Callisto into a bear. Years later, Arcus was hunting in the woods and came upon the bear. Not recognizing his mother, he prepared to shoot her. To prevent the matricide, Zeus intervened, turning Arcus into a constellation, Boötes, and placing him in the sky to watch over his mother, Ursa Major, for eternity. Arcturus is in a transition phase. It is currently ascending the red giant branch. Eventually, it will undergo a helium flash, a sudden, violent ignition of helium fusion in its core. After that, it will shrink slightly and become a stable helium-burning star for a while. But its fate is sealed. It is not massive enough to explode as a supernova. Once the helium is gone, Arcturus will shed its beautiful orange outer layers, creating a glowing planetary nebula. At the center, the hot, dense core will remain as a tiny white dwarf, slowly cooling in the dark for eternity. Now, we move away from Arcturus. Its orange light remains prominent for a long time, like an ember suspended in the blackness. We've learned that brightness doesn't always mean youth, and that aging can be as majestic as the overflowing energy of young stars. Our journey is now approaching regions even closer. We will leave behind the serene old age of Arcturus to the next star. The next destination is not a single star, nor is it just a multiple system. It is the closest multiple system of all. We now crack the top 3. For this, we must return to the deep southern sky. We are looking for Alpha Centauri, also known as Rigil Kentaurus. This is the most personal stop on our journey. Why? Because this is our neighbor. Aside from the Sun, this is the closest star system to Earth, roughly 4.3 light-years away. In cosmic terms, it is right next door. From Earth, Alpha Centauri doesn't present itself as a spectacle for everyone. It is a jewel of the southern hemisphere, visible as a bright star in the constellation Centaurus. To the naked eye, it appears as a single point of stable, yellowish-white light, with no extreme colors or rapid flicker. For centuries, it was a key reference for southern sailors, a constant presence on the open seas. Nothing in its appearance suggests that we are observing the star system closest to the Sun, nor that behind that point lies a complexity that will completely change the emotional scale of our journey. As we get closer, Alpha Centauri ceases to be a star and becomes a multiple system, with not 2, but 3 stars. First up are Alpha Centauri A and Alpha Centauri B, 2 stars orbiting each other in a slow, precise dance. Alpha Centauri A is very similar to the Sun, yellow, stable, slightly larger, and luminous. Alpha Centauri B is slightly smaller, more orange, but just as stable. Then the third protagonist appears, Proxima Centauri, a small, red, faint star orbiting at a great distance from the main pair. Proxima Centauri does not shine majestically, but its importance is enormous. It is the closest star to our solar system, just over 4 light-years away. The setting is surprisingly familiar. There are no supergiants, no chaotic disks, and no extreme deformations. Alpha Centauri appears to be a habitable, orderly stellar neighborhood, where the rules resemble those we know. For the first time on the trip, we are not observing something radically alien. We're looking at something almost familiar. Being close to Alpha Centauri A and B is a reassuring experience. Its radiation is intense, but comparable to that of the Sun. Their surfaces exhibit star spots, cyclic activity, and magnetic variations reminiscent of those of the Sun. There are no devastating plasma jets or winds here that can sweep entire systems. It appears to be a place where the human race could thrive. Proxima Centauri, on the other hand, introduces a note of tension. It is an active red dwarf, prone to emitting powerful flares. These flares release large amounts of radiation over short periods, drastically altering their immediate environment. To be near Proxima is to experience a sky that can go from calm to violent in minutes. This contrast is key. In the same system, stability and danger coexist. On the one hand, the solar calm of Alpha Centauri A and B, and on the other hand, the unpredictability of Proxima C. Here, we understand that proximity does not guarantee safety, but it does guarantee a range of scenarios. The Alpha Centauri star system is approximately 4 light-years away, which, compared to the distances of the other stars we've talked about, doesn't sound so far away anymore, does it? With this information, Alpha Centauri turns interstellar travel into a project, not a fantasy. It also breaks a common idea that the nearest system would be strange or hostile. In reality, Alpha Centauri is surprisingly familiar. 2 stars similar to the Sun. A third is small and active. It is a distorted mirror of our own star system. Here, we recognize a fundamental truth. We are not isolated. We live in a stellar neighborhood where similar systems exist, where chemistry, physics, and structure are not unique. It reduces the feeling of cosmic loneliness, replacing it with one of unsettling proximity. Alpha Centauri is one of the most studied systems in the search for exoplanets, and rightly so. At least one planet has been confirmed on Proxima Centauri, Proxima b, a world of similar size to Earth that orbits within the so-called habitable zone of its star. This discovery changed everything. Proxima b receives an amount of energy comparable to that which the Earth receives from the Sun. In theory, it could harbor liquid water. However, the reality is more complex. Proxima's intense flares could erode its atmosphere and bombard its surface with radiation. Other planetary candidates have also been proposed in the system, although their confirmation remains uncertain. In Alpha Centauri A and B, the search continues. There may be planets yet to be detected, orbiting stars remarkably similar to the Sun. Alpha Centauri doesn't promise us extraterrestrial life. Still, it does offer us something just as powerful: the real possibility of finding it nearby, not in a distant galaxy, but in the neighboring star system. When we move away from Alpha Centauri, the feeling is unlike any we've had before. We do not leave behind something strange or unattainable. We leave behind a possible home of the human race of the future. A destiny that one day could cease to be imaginary. Our journey continues, but now we are burdened with a question that will not go away. If there are worlds out there so close, what does our place in the universe really mean? The course continues, and the brilliance that awaits us next is not defined by proximity or possibility, but by pure power. We are now heading towards a star that dominates the southern sky because of its real energy, not because of its distance. The silver medal goes to a star that is legendary among navigators, but often unknown to city dwellers in the north. This is Canopus, the second brightest star in the night sky. Located in the constellation Carina, the keel of the great ship Argo, Canopus is a beacon of the southern hemisphere. When viewed from Earth, Canopus is not intimidating. To observers in the southern hemisphere, it appears as a stable, white star, bright but without the drama of other celestial lights. It does not blink violently or stand out for an extreme color. In the northern hemisphere, at many latitudes, it simply does not exist, always hidden below the horizon. For centuries, Canopus was a navigational star, a reliable reference on the open seas, especially in the deep south. Nothing in its appearance suggests that we are observing one of the most powerful stars in our galactic neighborhood. As we get closer, the true nature of Canopus is revealed with unnerving clarity. Canopus is located about 310 light-years away. In other words, their brightness is not due to proximity. What we see from Earth is only a fraction of its actual power. It sits on the border between A-type stars, like Vega, and F-type stars, like Procyon. It is white to yellowish-white, burning at a surface temperature of roughly 7,000 to 7,500 Kelvin. While the Sun is a dwarf and Betelgeuse is a supergiant, Canopus is a bright giant. It is a star that has exhausted its core hydrogen and ballooned outward, but it has not yet reached the tenuous, bloated dimensions of a red supergiant. The sheer luminosity of Canopus is staggering. It shines with the visual brightness of approximately 10,700 to 13,000 suns. Canopus is a puzzle for astrophysicists studying stellar atmospheres. Most stars, like the Sun, have a corona, a superheated outer atmosphere that emits X-rays. Cool giants usually do not. Canopus sits right on the dividing line. It has a corona that is heated magnetically to millions of degrees, making it one of the few giants known to emit X-rays, although the mechanism for how it sustains this magnetic activity is still debated. While ancient sailors used Canopus to navigate the oceans, modern engineers use it to navigate the solar system. Canopus holds a unique distinction. It is the most important navigational star for spacecraft. But why Canopus? Because when a space probe like Voyager, Galileo, or Cassini navigates the dark reaches between worlds, it must know which way is up to keep itself steady. To do that, the craft locks onto two reliable reference points. First, the Sun, which is easy to find because it is the brightest object, and a second distant star to prevent the probe from rolling around the Sun axis. Canopus makes an ideal second anchor. Its exceptional brightness makes it easy for sensors to detect, and its position near the south ecliptic pole places it almost perpendicular to the plane of the solar system. As the spacecraft and the planets move, the Sun and Earth shift their positions, but Canopus remains roughly fixed in the probe's sky, providing a steady, dependable marker for orientation. When we move away from Canopus, its light quickly loses prominence. From afar, it looks like another star in the southern sky. But now, we know what it really is. A colossal energy engine, running without the need for attention. Our journey has changed scale. We already understand that power is not always announced with brilliance, and that understanding prepares us for the final destination. What follows is not merely power or merely proximity. It is the perfect convergence of both factors. The brightest star in the night sky awaits us. We have arrived. The final destination. The brightest star in the entire night sky. Sirius. Located in Canis Major, the Greater Dog, Sirius is often called the Dog Star. It is the jewel of the winter sky in the north and a piercing light in the south. With an apparent magnitude of -1.46, it outshines its nearest rival, Canopus, by a factor of 2. It is so bright that under exceptional conditions in high-altitude locations, keen-eyed observers can spot it even while the Sun is still above the horizon. But why is Sirius number 1? It is a combination of two factors: intrinsic brightness and extreme proximity. Sirius is located just 8.6 light-years from Earth. In the vast scale of the Milky Way, which is 100,000 light-years across, Sirius is essentially standing on our front porch. It is the 5th closest stellar system to the Sun. Because it is so close, we receive a massive amount of its light. When you look at Sirius through a telescope, or even with the naked eye, on a turbulent night, It doesn't just look white, it scintillates. It is the best example of scintillation, which means twinkling. When Sirius is low on the horizon, its light passes through a thick layer of Earth's turbulent atmosphere. This turbulence acts like a series of lenses and prisms, bending the light rapidly. The result is a strobe light effect where Sirius appears to flash red, green, and blue wildly. This phenomenon is so intense that Sirius is frequently reported as a UFO by concerned citizens who see a spinning, flashing object hovering in the sky. Sirius shines because it can, and because it is close enough for its power to reach us without diluting. But it's not until we get to his side that we discover that Sirius isn't a lone star. It is a binary system. Sirius A is a bluish-white star, about twice as massive as the Sun and several times more luminous. It shines with the visual brightness of about 25 suns. It burns at a searing 9,940 Kelvin, compared to the Sun's 5,778 Kelvin. This higher temperature gives Sirius its distinct blue-white color. While the Sun is a G-type yellow dwarf, Sirius is a hotter, fiercer engine. It burns its hydrogen fuel much faster than the Sun. While the Sun has a lifespan of 10 billion years, Sirius will only live for about 1 billion years before running out of fuel. Currently, it is roughly 200 to 300 million years old, a young, energetic star in the prime of its life. Orbiting it is Sirius B, affectionately known as the Pup. The Pup is a white dwarf, the first of its kind ever discovered. It is a tiny, incredibly dense remnant, packing the mass of the Sun into the size of the Earth. This meant Sirius B was impossibly dense. A teaspoon of matter from Sirius B would weigh more than 5 tons on Earth. Sirius B became the first discovered white dwarf, the dead core of a star that has shed its outer layers. It is a stellar corpse, slowly cooling in the dark. Its discovery revolutionized physics, forcing scientists to develop the theory of degenerate matter in quantum mechanics to explain how such a star could exist without collapsing into a black hole. No star has influenced human history quite like Sirius. Its brightness made it impossible to ignore, and its cycle became the heartbeat of ancient timekeeping. To the ancient Egyptians, Sirius was known as Sopdet, or Sothis to the Greeks. Its role was agricultural and existential. Egypt depended entirely on the annual flooding of the Nile to fertilize the land. Around 3000 BC, Egyptian priests noticed a coincidence. The Nile flood began almost exactly when Sirius rose in the dawn sky just before the Sun. This event is called the heliacal rising. For roughly 70 days, Sirius is hidden behind the glare of the Sun. In midsummer, round July, it finally peaks above the eastern horizon just minutes before sunrise. When the Egyptians saw Sirius return from the underworld, they knew the floodwaters were coming. They based their calendar, the Sothic cycle, on this star, making it the foundation of the 365-day year we use today. The name Sirius comes from the ancient Greek word seirios, meaning glowing or scorcher. Unlike the Egyptians, the Greeks and Romans feared the star. They noticed that Sirius rose with the sun during the hottest part of the summer, late July and August. They believed that the heat of the star combined with the heat of the sun to create oppressive, feverish weather. They called this time the Dog Days. Ancient writers like Homer and Hesiod describe Sirius as a bringer of drought, fever, and madness. If the star twinkled violently red, they believed it signaled a year of war and strife. But Sirius also corrects a common idea. It's not just the brightest. It's close. It's massive. It's binary. It's evolutionarily complex. It is not a visual accident. It is a cosmic node, a place where physics, human history, and perception align. On our journey, Sirius is the climax because it doesn't need exaggeration. It's exactly what it sounds like, the brightest star in the night sky. So far, no exoplanets have been confirmed around Sirius. The reason is complex. The presence of Sirius B implies that the system went through a violent phase in the past. The star we see today as a white dwarf was, at the time, a giant that lost a large amount of mass. That process would have altered any nearby planetary systems, expelling worlds or destroying them. As we move away from Sirius, its light remains the last to fade. Even when the rest of the stars melt into the distance, Sirius remains, like a beacon that refuses to go out. It is the king of the night, the fire in the dog's mouth, and the worthy champion of our journey. We have traveled from the spinning river's end of Icanar to the blinding diamond of Sirius. We have seen dying giants, dancing twins, and dusty infant solar systems. We view the solar system with a different understanding. We know that the sky is not a backdrop, but a living archive of stellar stories. Sirius is not the end of the universe, but it is the end of this journey. When you look up tonight, you aren't just seeing static points of light. You are seeing a history of the universe. You are seeing neighbors and monsters.